So previously we have considered exponential trigonometric functions in terms of complex numbers. For example, cosine c can be written as cosine x plus iy. And we have seen that we can apply the addition theorem for the trigonometric functions. Then it becomes cosine x cosine iy minus sine x sine iy, which is cosine x cosine hyperbolic y. Am I loud enough? Is my voice loud enough? How about in the back side? Can you hear me well? If you have trouble like hearing me or understanding me, then just raise your hand and let me know. I sine x sine hyperbolic y sine z is sine x plus iy sine x cosine iy plus cosine x sine iy, which is sine x cosine hyperbolic y plus cosine x sine hyperbolic y with an I in front of the argument. And actually, the previous class I introduced cotangent z, right? And I misspelled this tangent z, so I just make sure that those errors need to be compensated. And that can be rationalized by multiplying cosine z complex conjugate, sine z, cosine z complex conjugate. And because we don't have enough space, maybe in the next page. The mistake, let me just check right. X, Y. Right. Once we made a mistake, then it's very difficult to reverse it. So cosine, 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 cosine. So tangent z is cosine z sine z. It can be rationalized. The denominator can be rationalized by multiplying cosine z complex conjugate, sine z, cosine z complex conjugate. The denominator, this is called denominator. In Korean is 분모, and this nominator. In Korean, it's called 분자. So you are learning English as well while learning mathematics. It's good for you, right? So denominator is cosine z times cosine z complex conjugate is cosine z cosine hyperbolic z minus I sine z sine x x y y just y. Complex conjugate is you just change the sign of the imaginary number. So it's cosine x cosine hyperbolic x plus I sine x sine hyperbolic y y. Cosine square x cosine hyperbolic square x plus sine hyperbolic square y sine hyperbolic square y, right? Cosine x squared can be written as 1 minus sine square x cosine hyperbolic square x plus sine square y sine hyperbolic square y. So this is cosine hyperbolic square x minus cosine hyperbolic square x minus sine hyperbolic square y sine square x, right? And you probably learned in your high school days that cosine hyperbolic square y minus something is wrong. Right. I think I made a terrible mistake. This must be y, right? X. This must be y. This must be x. Therefore, let me just double check. So that's cosine square x cosine hyperbolic square y plus sine square x sine hyperbolic square y, right? So that is 1 minus sine square x cosine hyperbolic square y plus sine square x sine square y. So it's cosine hyperbolic square y minus sine square x cosine hyperbolic square y minus sine hyperbolic square y. And this is 1, right? And sine square x plus cosine square x is equal to 1, right? So this is cosine hyperbolic square y minus sine square x is actually 1 minus cosine square x. So this is cosine square x plus cosine hyperbolic square y minus 1. How about nominator? Nominator can be a little bit more complicated. So I proceed because I think there's just double check the denominator cosine sine. to sine z cosine z complex conjugate, which is sine x cosine hyperbolic y plus I cosine x sine hyperbolic square y cosine x cosine hyperbolic square y minus I sine x sine hyperbolic square y. Let me just check each term. Okay. So that is, the real part is sine x cosine hyperbolic square y plus sine x cosine x sine hyperbolic square y. Let me check. Let's check term by term. So sine z times cosine z complex conjugate. So sine z is, I made a mistake, right? Complex conjugate is plus. So I have been teaching this class for a while, but still I made a mistake. So that's the wisdom you learn from me, that you have to practice at home. So it's sine x cosine hyperbolic y plus I cosine x sine hyperbolic y times this. So we have minus sign here, right? Plus complex cosine square x sine hyperbolic y cosine hyperbolic y plus sine square x cosine hyperbolic square y sine hyperbolic square y. So it turns out that it's sine x cosine x plus I sine hyperbolic square y cosine hyperbolic square y. So tangent z is sine x cosine x plus I sine hyperbolic square y cosine hyperbolic square y and cosine square x cosine hyperbolic square y minus 1. And actually, in previous class, I derived the cotangent z. So I think the only thing you need to do is secant z and cosecant z, right? And hyperbolic function can be also derived a similar way, that cosine hyperbolic z, definition is 2 over exponential z, exponential minus z, right? So exponential z is exponential x plus iy. So this is e to the x, e to the iy, e to the x cosine y plus I sine y e to the minus z is e to the minus x minus iy e to the minus x e to the minus iy e to the minus x cosine y minus I sine y. So e to the z plus e to the minus z is cosine y e to the x plus e to the minus x, right? Plus I sine y e to the x minus e to the minus x. So 1 over 2 e to the z plus e to the minus z is cosine y 2 over 2x plus 2 to the minus x, right? Plus I sine y 2 to the 2x minus x is cosine hyperbolic x cosine y plus I sine hyperbolic x sine y. So let's make a comparison that this is cosine hyperbolic c. So hyperbolic c is cosine hyperbolic x cosine y plus I sine hyperbolic x sine y. On the other hand, cosine z was cosine x cosine hyperbolic y, right? Minus I sine x sine hyperbolic y. So just for the fun of it, consider cosine iz and see what happens. That is cosine I x plus iy, right? And this is cosine ix minus y, right? So applying the addition theorem, we have cosine ix cosine minus y minus sine ix sine minus y, right? So this is cosine hyperbolic x cosine y minus I sine hyperbolic x minus sine y, which is cosine hyperbolic x cosine y plus I sine hyperbolic x sine y. Which is which is cosine hyperbolic z, right? So we also have a very interesting relation that cosine iz is in general cosine hyperbolic z. So this is very important to result. So we can assume the same relationship will hold for sine, right? So question. Sine So this can be actually a very good quiz problem. It's a good candidate. But as a bonus, I'm going to show this today. So, oh, by the way, next Wednesday, we don't have a class, right? It's 추석 holiday. So let's see, check. By definition, 2 to the z minus 2 to the minus c, right? So as before, 2 to the z is 2 to the x plus iy. This is 2 to the x, 2 to the iy. And you can apply Euler's theorem, Euler's formula. Cosine y plus I sine y. So this part is Euler's formula. And 2 to the minus z is 2 to the minus x minus iy is 2 to the minus x exponential minus iy minus x cosine y minus I sine y. So 2 to the z minus 2 to the minus z is 2 to the x cosine y plus I sine y minus 2 to the minus x cosine y minus I sine y. So we have cosine y 2 to the x minus 2 to the minus x plus I sine y 2 to the x plus 2 to the minus x. So if you divide by 2 over exponential z minus exponential minus z is cosine y, cosine hyperbolic, not cosine, sine. Sine hyperbolic x plus I sine y cosine hyperbolic x, which is sine hyperbolic c. Copy, delete, paste. I can move this here. And sine iz sine ix minus y, right? Which is sine ix cosine minus y minus cosine y plus cosine minus y what am I doing? Cosine ix sine minus y. So this is I sine hyperbolic x cosine y minus cosine hyperbolic x sine y which is I sine hyperbolic x cosine y plus I sine y cosine hyperbolic x, right? So this is I sine hyperbolic c. So in complex domain, the trigonometric function and hyperbolic functions are related to each other by I. So sine iz is I sine hyperbolic c. So far, this polynomial functions and trigonometric functions and hyperbolic functions are all single valued. By the way, polynomial functions trigonometric functions hyperbolic functions. Hyperbolic functions mean also exponential functions. Also. Single valued. Single valued function. That means one input for one output. So a good example of a single valued function is a vending machine in the outside of the classroom. You put coin, you get coffee, right? You never get 2 cups of coffee out. Do we? You put money and you get your coffee out. But you get only 1 cup of coffee, right? I mean, it'll be very nice if you can get 2 cups of coffee for the same amount of money, but it never happens. So vending machine is a very good example of a single-valued function. So when you have one output for all possible input, it's called single-valued function. Inverse function of exponential function. E to the z. So inverse function is called 역함수. And probably you have learned that function in your high school days. Anybody remembers? The inverse function of an exponential function. In your the freshman in high school, first year, log, right? Logarithmic function. So let's say W is log Z. And say U I3 XY. And U, V are real function. Then Z is exponential W, right? Exponential U plus I3. Exponential U cosine 3 plus I sine 3. Z complex conjugate also equal x plus IY. You can Z in terms of x and y. Then this is what? X plus IY, x minus IY, x squared plus y squared is R squared. So we defined this way in previous class that xy, this is R, right? This is theta. So z squared is actually exponential 2u cosine square v plus sine square v. Exponential 2u is R squared. Exponential u is R. So u is nothing but log R, log Z. What is v? V is nothing but theta, right? We have set log Z as a u plus I3, and u and v are real functions. Inverse function Z is exponential W, and can be written as exponential U times cosine V plus I sine V. And also this is Z can be written as x plus IY. the absolute value of z is x squared plus y squared, and we call this r variables. Then absolute value of z squared is same as exponential 2u. Cosine square of v plus sine square of v is actually exponential 2u, which is r squared. So exponential u is nothing but r. Then u is log r, which is the same as log absolute value of z. What is phi? Phi is nothing but theta. But then there is a trouble comes out. So we can actually write down log z is log absolute value of z plus I theta. When z r exponential I theta, right? If theta is theta plus 2 pi, what happens? In other words, let's say theta prime, theta plus 2 pi, and z prime is r exponential I theta prime. R exponential I theta plus 2 pi R exponential I theta exponential I 2 pi. Exponential I 2 pi is equal to cosine 2 pi plus I sine 2 pi. Sine 2 pi is equal to 0. So it's actually, this becomes 1, right? So z prime is z, right? When you increase the argument theta by 2 pi, the z doesn't change, right? On the other hand, log z prime, that is log z prime plus I theta prime. Z prime is same as z, right? But this theta plus 2 pi, which is not the same as the log z, right? So if you increase the argument by 2 pi, the z doesn't change, right? It's practically the same. But the resulting logarithmic function is not the same, right? So we have very important lesson that logarithmic function is not single valued. Let you copy. And actually this topic is a very important one, so maybe we can take a break and continue discuss next. after the break. So any questions about the previous content about single valuedness versus multi-valuedness? This is very important concept. We found that logarithmic z can be written as a log of absolute value of z plus I theta. Theta is actually argument of z, right? So we can also write down in polar coordinate that z can be written as r times exponential I theta. But if we turn around once again, once more, then we get extra 2 pi, right? If we run the counterclockwise rotation again, once again, then you add 2 pi. Whenever you circle around, you add 2 pi. So if you add n times, you can have 2n pi. Then, if you rotate theta by adding 2 pi, and we call this z prime. The z prime is r times exponential I theta prime, which is r times exponential I theta 2 plus 2 pi. But exponential 2 pi I is equal to 1. Exponential 2 pi is cosine 2 pi plus I sine 2 pi. Cosine 2 pi is equal to 1. Sine 2 pi, 0, right? So we added 2 pi, and let's denote this as z prime. But it turns out that because exponential 2 pi is just equal to 1, it's the same as z, right? So z prime is same as z. But, so z and z prime can be considered as the same point in z plane, right? But logarithm of z prime is differed by 2 pi I. It's not the same as log z, right? So we say log z is not single-valued function. And in that case, the center of rotation is c equal to 0, right? Which is center of rotation is called branch point. So most general representation of a logarithmic function is let's confine theta principal value from 0 to 2 pi and log z log absolute z plus I theta plus 2k pi. K is 0 plus minus 1 plus minus 2. So how many? How many different values of logarithmic for log z? Infinite. So log z is not a very good, it's not single-valued function. it's hard to breathe with the mask, especially when I give a talk, lecture. Another good example is the following. C prime is C times exponential 2 pi I is same as Z, right? What happens if you take the fractional power, Z to the half? Let's say square root of Z. How about Z prime to the half? Z exponential 2 pi I 1/2 Z to the half exponential I pi minus square root of Z, right? And exponential I pi is -1. So fractional power is also the case for but not single-valued function. So multi-valued function. The general case, Z to the A. It can be written as exponential A log Z, right? You probably learned in high school. Say x to the A, e to the A log x. It's probably one of the, how do you call it? Anybody familiar with 수학의 정석? No? You use a different one? So 수학의 정석 was like a standard mathematical reference when I was in high school. And there was like an example called 필수예제. And one of the 필수예제 was this, show this. So exponential A to the log Z plus I theta P plus 2K pi, right? What if A is complex? Exponential A1 A2 log Z I theta P plus 2K pi exponential A1 log Z minus A2 theta P plus 2K pi times exponential I A2 log Z plus I A1 theta P plus 2K pi maybe I should make a copy of this. Copy, paste. So it's z to the a. So this is exponential a1 log c minus a2 theta p plus 2k pi times cosine a2 log z a1 theta p plus 2k pi plus I sine a1 a2 log c plus a1 theta p plus 2k pi. Wow. Looks complicated. So using this formula, we can actually represent z to the I or z to the, complex power. You can define complex power. For example, c to the a, i's. What is this I? So this is example. This is a1 is equal to 0. a2 is equal to 1, right? So z to the I is actually exponential minus theta p plus 2k pi times cosine log c plus I sine log z. So you can express the complex power of complex number. So at this time, probably I'll give you homework. A to the z. For complex I. So this is homework, your homework. Check at home. So homework means you do at home, right? But you don't have to give it to me. Another case of multi-valued function is inverse functions. But I will let you copy the screen. So anybody seen the complex power, raise your hand. So probably this is your first time to study the complex power of a complex number, complex function. So sine inverse C, inverse sine function. So let's consider inverse sine function. Then z is sine w, right? Which is 2I times exponential iw minus exponential minus iw. Or exponential iw minus 2iz minus exponential minus iw is equal to 0. So we multiply exponential minus iw on both sides, then what do we get? Exponential 2iw minus 2iz exponential iw minus 1 is equal to 0, right? Or exponential iw square minus 2iz exponential iw minus 1 is equal to 0. This is a quadratic equation you learned in middle school. 2차 방정식, right? Parabola equation. And so you can find the root, right? Exponential iw is iw plus 1 minus c square root. Right? Or no, not WC. IZ. Let me see. Oh, I think I made a mistake. IZ plus minus c square plus 1, right? Which is same as I c square minus 1 to the half I c plus c square minus 1 half. Let me see. So exponential IW is I c plus c square minus 1 to the half. So IW is log I z plus z squared minus 1 to the half. Or w is 1 over I rho I z plus z squared minus 1 to the half. So we briefly described how to define functions. And so we are repeating that you're a freshman in high school, that you learn different kind of functions. And then what did you learn after you learned about functions? Differentiation, right? Derivative. I think most of you have learned in calculus during high school and freshman at the university, but probably also you forgot, right? You forgot most of the derivatives. So I'll just give you maybe half an hour crash course on derivative. So fx x0 in the region R if and only if there is epsilon and delta such that fx minus x0 is less than epsilon whenever x minus x naught is less than delta. It's the definition of a continuous function. In Korean, continuous function is called 연속함수. So continuity is about the small change of function around at some point. So we call function fx is continuous at x is x naught in the region R if and only if there is, actually there is a grammar error. There are epsilon and delta who's greater than 0 such that whenever x minus x0, x naught is less than delta, then the function is less than epsilon. This is the definition of a continuous function. It's actually one sentence, rather long sentence. And according to the basic grammar, there are 5 types of sentence in English, right? Type number 1, I am a boy, right? Subjective and verb, and the rest are the complements, C. So this is actually type 1 sentence, even though it is very long. Derivative is defined as following. dx df x at x0 is defined as the limit delta goes to 0, delta f x this is the definition of a derivative. So say, example, fx is called 1 over x. So what is the derivative? You learned minus 1 over x squared, right? So let's check. dx dfx is, by definition, one over delta f x plus delta minus fx, right? So this is, you don't have to memorize actually, 1 over delta x plus delta minus 1 over x. Delta goes to 0, 1 over delta x plus delta x minus x plus delta, which is minus x plus delta, which is minus 1 over x squared. This is obvious. Probably in high school days you just memorize. How about sin x? If you take a derivative of sin x, what do you get? Cosine x. But most likely you also memorized in high school, right? But actually that can be derived. Just in case. So just for the statistics, how many of you have, anybody who is not taking calculus, raise your hand. You didn't not learn differentiation, integration, raise your hand. So you know the basic calculus, right? At least. Because sometimes I have a student from like Korean literature or piano music attending my class who doesn't have the major open class, calculus class. They might have difficulty in following the class. So, but I'm trying to make this class as self-contained as possible, so to cover some brief things. So just for sine, so when we have fx is equal to sine x, fx plus delta sine x plus sine plus delta, right? So using trigonometric addition theorem, you can write down sine x cosine delta sine delta cosine x. So fx plus delta minus fx over delta is sine x delta over cosine delta minus 1 plus cosine x delta over sine delta. So we need to find out what is sine delta for small delta, right? So I'm just trying to follow what Newton did in the 17th century. So it's Newton's approach. In 1650, you draw a unit circle with the radius 1. So this is 1. Say this angle is delta. So what is this length? Okay, go back to your maybe 7th grade. I mean, in middle school freshman year. You learned about circle. Say this is r, this is theta, this is r theta, right? This is arc length. So, because the radius is 1, this arc length is just delta, right? And for sufficiently small delta, we can actually use a magnifier so that we can actually, this is delta, this arc is delta, but we can slightly extend this, make a triangle. And then this length is approximately delta 2 for small delta. So that means for small delta, we approximate height over triangle by the arc length delta. And what is this length? Square root of 1 plus delta square, right? So in that case, it actually works for very small delta. And that's what actually Newton did about 380 years ago to derive the formula for the derivative of sine x. Then you should have a very good drawing for this. So mathematics and art has one common terminology. And this is supposed to be a joke in Korean. 그린다? 그리다? So, okay. So actually, this is arc length and slightly delta. This is delta actually. Then this is 1. This is 1 plus delta square, and this is delta. Then sine delta is approximately 1 plus delta square over delta. And cosine delta approximately 1 plus delta square over 1. Also, Newton made another simple approximation. Epsilon to the 1/2 is approximately 1 plus epsilon over 2 for small epsilon. And this formula is very useful if you remember that. Maybe you can check. 1 plus 0.1 Anybody has a calculator? 1.1 to the square root of 1.1? Approximately 1.05, but actual value. 1.0. You can answer in Korean. For something 104842 something, right? It's close to 1.5. How about 1.001.1F? Okay, I would say 1.005. Actual value 1.00498. It's getting close to, right? So as epsilon become very small, the square root of 1 plus epsilon is saying is you can write down 1 plus epsilon 2. It's a very useful formula to remember that. So using this knowledge, delta over sine delta is 1 over delta square root of 1 plus delta square over delta, right? And luckily this cancels each other and it becomes 1, right? As delta goes to 0. And actually this formula has a name. L'hôpital의 정리? It's French, l'hôpital. So what else do we have? So delta over sine x plus delta minus sine x is delta sine x cosine delta plus sine delta cosine x minus sine x, right? So it becomes sine x delta over cosine delta minus 1 plus cosine x delta over sine delta. Cosine delta minus 1 is square root of 1 plus delta square over 1 minus 1, right? So this is 1 over delta square root of 1 plus delta square 1 minus square root 1 plus delta square. And it's approximately 1 over delta square root of 1 plus delta square, 1 minus 1 plus delta square over 2, right? So it becomes minus 2 times 1 plus delta square over delta. And it becomes 0, right? As delta goes to 0. So dx d sine x is cosine x. So you don't have to memorize it anymore. You just find out how to derive this formula. And actually Newton did about 400 years ago, using simple geometry and approximate formula for the square root. Another number that you need to remember is this, 1 plus epsilon over 1 over epsilon. It becomes E. It's called Napier's number, right? It's 2.718 something. So maybe just for the curiosity, let's just check 1.01 over 100. I think 2.7 something. 2 point? Zero 4. Oh. So when epsilon becomes 0, it becomes Napier's number. That can be used to derive the log in fx. Just function and let's take a break. So fx log x. Fx plus delta minus fx log x plus delta minus log x log x plus delta log 1 plus delta over x, right? So delta over fx plus delta minus fx is simply 1 over delta log 1 plus delta over x, right? And then actually you can divide by x and multiply by x. Log 1 plus delta over x, and it becomes 1 over x log 1 plus delta over x over delta over x. And this becomes E. So it becomes 1 over x. So maybe it's a good time to give you another homework. Fx is a to the x. I think you probably have done it in your high school days. It could be fun. And let's take a break for maybe 5 minutes and continue. So in complex domain, complex functions, analytic function is very important notion. So of a complex function, Fz is called analytic if Fc is differentiable and single valued. So two things are the necessary and sufficient condition for function Fc to be analytic. One is differentiable and single valued. So some of the functions we considered so far, such as logarithmic function or with the fractional power, is not an analytical function. It's differentiable means if exists and is unique. Another definition for complex function is differentiability. So two things are important. One is a function is analytic. It's differentiable and single valued. And secondly, differentiable means this limit exists and is unique. So uniqueness is a very important condition, and we are going to see what does that mean shortly. So Fc U x y I v x y U and v belongs to real. That is real functions. And delta z, delta x plus I delta y. So two things are very important. So today we learn very difficult concept called single valuedness, right? This is actually quite difficult concept, and I think probably you'll understand after maybe taking a quiz. Until then, it's still confusing. And maybe some of you are still confusing even after quiz. But the analyticity and differentiability is quite obvious. maybe. This is just an analogy. So you have a vending machine. You put coin and you select button, right? And pops out. Okay, say Z is 501 coin made in 2000. Z prime is 501 10 pi. Doesn't make sense, right? Different year. Okay. We can take an analogy for Z as a coin, 501. And adding 2 pi is like when coin is made in different year. Okay? So, but it's still saying 501, right? But you can distinguish still. For single valued vending machine, it doesn't matter whether you put Z or Z prime, you get just 1 cup of coffee. But if we have a multi-valued vending machine, it's a very strange machine. If you put this coin, you get just 1 cup of coffee. But on the other hand, if you put the different coin made in different year, you get 2 cups of coffee. It's not, I don't know. Just cartoon expression for single valued and multi-valued expression. So Z is like the original coin made in 2000. And Z prime is you just turn around the circle. It's like a probe pi. So 2 pi. 2006. 2 pi is 2006. Okay, let's say pi is 3. So this coin is made in time about 2 pi year after 2000. In terms of the amount of money, it's the same, right? The same 501, whether the coin is made in 2000 or 2006. So single valued vending machine, it doesn't make any difference. It doesn't differentiate. You can use either coin. You still get 1 cup of coffee. But somehow you have a multi-valued vending machine that is different output, given the same amount of money. Coin Z produces 1 cup of coffee. On the other hand, coin Z prime produces 2 cups of coffee, even though the same amount of money because it was made in different time. So 2 pi separate by 2 pi years. Is it good analogy for this understanding the single value versus multi-value functions? I hope it does. It would be very nice to have this multi-value vending machine, isn't it, right? So you can have 2 cups of coffee for the same amount of money, just make it different years. Where were I? Okay, so let's go back to this differentiation. So f z plus delta z minus fz divided by delta z, which is the following. Delta x plus I delta y, u x plus delta x, y plus delta y, plus I free, x plus delta x, y plus delta y, minus u xy, minus I free, xy. So we can separate the real part and imaginary part. Ux plus delta x, y plus delta y, minus uxy, plus I, delta x plus I delta y, free x plus delta x, y plus delta y, minus free xy. And there are 2 possible ways to make the path. So how do we make delta z goes to 0? We have 2 possible paths. One is we set delta x is equal to 0 and let delta y equal to 0 set. Another path is let delta x goes to 0 while set delta y set equal to 0. So there are 2 possible ways to approach delta z equal to 0. And the condition for the differentiability means requires that the final result are unique, is unique. So I'm going to use this copy. And next page. So this is what? This delta z. The path number 1. We set delta x equal to 0 and let delta y goes to 0. Right. So this is same as this. I delta y, u x y plus delta y minus u x y plus I delta y free x y plus delta y minus 3xy. And it becomes what? 1 over I delta y delta u plus this I cancels each other, delta y delta v. So this is minus I delta y delta u plus delta y delta v. This is pass 1. And okay, I'll make a copy of this again. Copy and delete. And next page. This is 1. 1 and 2 should be the same, right? And path. And path 2, we set delta y equal to 0 and let delta x goes to 0. Then delta z over f c plus delta z minus fc is this delta x u x plus delta x y minus u x y plus I delta x free x plus delta x y minus free x y, which is partial x partial u plus I partial x partial free. And these two results should be the same, right? If the derivative is supposed to be unique, then this is 2. For unique derivative, dz dfg, 1 should be same as 2, right? So partial x partial u plus I partial x partial v must be same as partial y partial u plus partial y partial v. So that means partial x partial u should be same as partial y partial v, and partial x partial v is same as minus partial y partial u. This is a condition for the derivative is unique. And this is actually called the condition for that function is analytic. So if the function satisfies this condition, it's called Cauchy-Riemann condition. It has a name. Cauchy-Riemann condition. And probably one of the few formulas that you need to memorize. Cauchy-Riemann condition is for the Fz exists. So Fz is analytic. We say CR condition. Fz is analytic if and only if Fz satisfies Cauchy-Riemann condition. Maybe I'll just write it down in the full name. Cauchy-Riemann condition and single valued. Example. So any questions about Cauchy-Riemann condition? That is the uniqueness of the derivative existence of uniqueness derivative. Example. Fc is z square, which is x square minus y square plus 2ixy. So u is actually x square minus y square, free is 2xy. So partial x partial u is 2x, right? Partial free y partial free is 2x. So partial x partial u is same as partial y partial v. On the other hand, partial x partial v is 2y. Partial y partial u is minus 2y. So that means partial x partial v is minus partial y partial u, right? So that means z square satisfies Cauchy-Riemann, right? And also single valued. Therefore, analytic. Example of FC which is not analytic. Z complex conjugate x minus iy. So u is x, v is minus y, right? So partial x partial u is 1, partial y partial v is minus 1, not same as partial x partial u. So this function is not analytic. Maybe just one more example. Sin z. Sin x, cosine hyperbolic y, I cosine x, sine hyperbolic y, right? So u is sine x cosine hyperbolic y, v is cosine x sine hyperbolic y. Partial x partial u, cosine x cosine hyperbolic y, partial y partial v, cosine x. And if you differentiate sine hyperbolic y, what do you get? Cosine. Right? Same as partial x partial u. Partial x partial v is minus cosine sine x sine hy. Partial y partial u is sine x. And cosine hyperbolic y, if you differentiate, you get sine. sine hyperbolic y, which is minus partial x partial v. So sine z satisfies CL condition. And dz d sine z is same as partial x partial u plus I partial x partial v, which is cosine x cosine hyperbolic y and minus I sine x sine hyperbolic y, which is cosine z, right? So actually, the relationship for the derivative is the same as in the case of a real case. And most likely quiz problem, I'll give you a homework. Here. Tangent C. U and V are quite complicated, right? I think at home, to show this Cauchy-Riemann condition for tangent Z will take about 1 hour for you, and maybe 10 pages of a note. And I usually prefer to give this problem for quiz with either tangent Z or cotangent Z. So either problem takes about, I think, 1 hour. So the best time to do the homework is when you stood up in the blind date. You wait at the coffee shop for your partner who is not going to show up. So what do? You just solve this. You can easily spend 1 or 2 hours. If you try to find the Cauchy-Riemann condition for tangent Z plus cosine tangent Z, you can spend 2 hours very easily. So actually, even though you stood up, you still gain something. So this is good homework, I think. And probably I'll stop here today and have a very nice 추석 holiday. The next Wednesday we don't have a class. 다음 주는 수업 없어요. 그래서 추석.